Hello everyone, and welcome to our channel Mootechie. It's wonderful to have you here with us today as we dive into a fascinating and fundamental topic in chemistry, buffers and derivation of Henderson-Hasselbalch equation. Get ready to unlock the secrets of how solutions maintain their balance. Let's begin by understanding what a buffer is. A buffer is a solution that resists the change in pH. This special ability comes into play when a small amount of acid or base is added. So what is a buffer made of? Well, it is composed of a weak acid and its conjugate base, or alternatively, a weak base and its conjugate acid. Now let's move on to the two main types of buffers. First, we have the acidic buffer, which maintains a pH of less than 7. It is made of a weak acid and the salt of its conjugate base. A classic example is a solution of acetic acid, or CH3COOH, mixed with sodium acetate, CH3COONA. Then we have the basic buffer, which maintains a pH greater than 7. This one is made of a weak base and the salt of its conjugate acid. A common example is ammonia, NH3, combined with ammonium chloride, NH4Cl. Next, we explore a very important equation that provides a relationship between the pH of acids and their pKa. This powerful tool allows us to calculate the pH of a buffer when the concentration of a weak acid and its conjugate base, or a weak base and its conjugate acid, is known. Coming up, we'll discuss the derivation of this key relationship, known as the Henderson-Hasselbalch equation. The equation is pH equals pKa plus log of the concentration of A minus divided by the concentration of HA. It can also be written as pH equals pKa plus log of the concentration of the conjugate base divided by the concentration of the weak acid. The reaction at the heart of this is HA plus H2O in equilibrium with H plus and A minus. From the law of mass action, we get the acid dissociation constant, Ka, which equals the concentration of H plus times the concentration of A minus, all divided by the concentration of HA. This is our equation 1. Following this, let's continue rearranging the equation to derive the final form. We start by isolating the hydrogen ion concentration. So we get H plus equals Ka times a ratio of HA over A minus. The next step is to apply the negative logarithm to both sides. This gives us negative log of H plus equals negative log of Ka times HA over A minus. Using logarithm identities, we can expand this to negative log of H plus equals negative log of Ka minus log of HA over A minus. Now we recognize that negative log of H plus is pH and negative log of Ka is pKa. This allows us to write pH equals pKa minus log of HA over A minus. Applying one more log identity, we finally arrive at our goal. pH equals pKa plus log of the concentration of A minus divided by the concentration of HA. Or more generally, pH equals pKa plus log of the concentration of the conjugate base divided by the concentration of the weak acid. As we continue, let's understand the real-world significance of the Henderson-Hasselbalch equation. This equation is crucial for calculating the pH of buffer solutions. It is incredibly useful in designing buffers for biological systems where a stable pH is essential for life processes. The equation also predicts the effect of dilution or the addition of acid or base on a buffer's pH. And it is profoundly important in understanding blood pH and medical conditions like acidosis and alkalosis. Thank you. See you in the next class. Author, Mootechie.